So we introduced parametric equations and parametric curves last time, and we did a example with a cubic function and a quadratic function. Let's use trig functions to start off with today. And right away, I'd like to do a more interesting example than just a plain old circle or ellipse, though I will talk about circles and ellipses. I'd like to do an example called a Lissajous figure because it's more interesting. The math of a Lissajous figure is harder, but it's a bit more interesting than just a plain old circle or a plain old ellipse. You still use trig functions to parameterize it, so your parametric equations still use cosines and sines. However, you make the frequency of the waves for x and y different. And it works out nicest if you pick the coefficients of t to be prime numbers that are small and different from each other. Like cosine of 3t, say, for x, and sine of 5t, say, for y. Again, the conceptual points that I make here, first of which being that you can think of this system of parametric equations as one point equation. These conceptual things are important. We should also give names to these functions. This one's going to be f of t. This one's going to be g of t. So I can think of those as two separate equations, but I can combine them into a single point equation where the components are f of t and g of t individually, which in this case become cosine of 3t, sine of 5t. You can call those individual functions component functions. You can also call them coordinate functions. Both names are okay. Components sort of hints more at the vector interpretation of this. Coordinates hints more at the fact that we're using rectangular coordinates. And we could use other coordinate systems like polar coordinates or something. But you can say either word. We want to graph this. I could make a table of values, say horizontally this time, if I wanted to. And if you did, I won't complete the table, but you'd probably want to start the table in the following way because we've got cosines and sines here. You'd probably want to choose inputs that are kind of standard angles in radians, like pi over 6, pi over 4, pi over 3, pi over 2, etc. And in fact, since the coefficients of t are bigger than 1, you might even want to choose smaller angles. I don't know, maybe like pi over 12, pi over 6, blah, blah, blah. I won't continue. Then for each of those values of t, which would be your ultimate independent variable, you'd find the corresponding values of x and y. And then you plot those x, y points in the plane for different values of t. Connect them with a smooth curve. But what really happens is it's really modeling motion. And so the drawings, while they're fine and they can be labeled with the different values of t, using your calculator to see the motion, or Mathematica, as I'm about to show you, is more ideal. So to start with a Mathematica, let's make a static picture that doesn't involve any motion. This is the kind of code you're going to want to use for the assignment and the one problem you make a printout for. I'm going to go ahead and define my f of t and g of t functions to start with. You actually can make the graph without bothering to define them. I'll explain how in a minute. But I'm going to define these functions. In Mathematica, when you define functions, you use, well, a function name, first of all, like f. Do not use parentheses for the input. Use square brackets, like you see. Put the variable name and an underscore when you are first defining the function. That is essential to put the underscore. If you don't put the underscore, it will not work right. You can just put an equal sign. I put a colon equals for reasons I'm not going to explain as a standard way, and they know about my explanation of reasons I'm not going to explain. It turns out to be most useful to do the colon equals in statistics, but I'm not doing it here. But I do make a habit, it's just out of habit of doing that even for functions. Cosine of 3t, the cosine, the c must be capitalized. If it's not capitalized, it won't work. Square brackets, 3t. I put a semicolon next. You actually can just tab to the next line. Semicolons, technically, what they do is they suppress output, but I like putting them between equations. Make g of t, sine of t, notice the capital S, notice the square brackets. What I'm about to do is something you do not have to do right now, but it's going to be really handy later on when we get to chapter 11 especially. And I'll even hint at chapter 11 right now by doing it now. I'm going to define yet another function, r of t, to essentially be the point valued function. What I wrote by hand will look like that. Except in Mathematica, don't use parentheses. Use curly braces, like this. Technically speaking, such an object is called a list in Mathematica. List can be interpreted in lots of different ways by Mathematica, depending on what you're doing. It can be interpreted as being a point. That's how we're going to interpret it initially. A vector. Just a list of quantities. Could even be a list of something else. It could be a list of graphs. I could put graphs inside of a list. That has actually some applications, believe it or not. Lots of things can go inside lists. Effectively, I'm thinking of this as a point. Semicolon there. I'm just going to go ahead and enter this as is. Notice these are all in the same cell. So when I enter by doing shift return, they all get entered at once. I had other things I've entered before this. So this says in 64 for input number 64. I've done 63 inputs before this point without closing Mathematica out. You don't need to worry about that. If I want to confirm, for example, that f of t is now stored in as the cosine function, I can type it in a new cell, do shift return, and there you see cosine 3t. G of t is sine of, oops, I made a mistake, didn't I? Forgot my 5. I forgot my 5, on purpose, I forgot my 5. Now I'm going to go back up there and re-enter it. It's okay, just re-enter it. Now it's right. And r of t, I can type that and hit enter, shift return. And there you see the r of t. Notice no underscores anymore. Once you define your functions, you don't need the underscores anymore. And in fact, it'll cause a problem if you use them. Notice there's also no underscores over here because I've already defined f and g, but I'm using those to define r. You might wonder, is anything stored in h of t? It depends on whether I've entered h of t before this. Probably not. No, nothing. I have not defined any function I called h of t. I could do that. I could do this kind of thing, e to the t, and now it's e to the t. Notice it's a capital E, but I don't want to do that. I can clear h by doing that, and now nothing is stored in h of t. And yes, you can go back and re-enter things, change things, re-enter stuff, and memory gets updated. Once I've got these functions entered, the key code, let me just cut these things out. By the way, I will also save these files on Moodle, so you can download them if you prefer not to take notes. The key code is parametric plot with 2 capital P's. Just a plain old plot will make just a plain old plot in the ordinary way, like in Calc 1 and Calc 2 for the most part. If you want to make a parametric plot, just like you have to change your calculator from function to parametric mode, here you have to use parametric plot instead of plot, because it's a different kind of plot. I can type the r of t here like this, put a comma, then a range of values for t like 0 to 2 pi. I can make the number pi by typing pi with a capital P. That's probably fastest. Or what's more fun, escape, P escape to make a fancy looking pi. Escape, P escape. Okay, so this is going to make a plot of this parametric curve. When you enter it, here it is, boom. That's the Lissajous curve. But you only are seeing the finished product, the final curve itself. You're not seeing the orientation of the curve, right? No arrows. You're not seeing how the curve is being traced out. You're not seeing the actual motion. Sometimes fast, sometimes slow. In fact, what happens here is the motion is fast where the curve is straighter, like for example in here, and slow when you're in kind of a tight curve like here. We will see that here in a minute. As far as your printout, this is all the kind of thing you need to do for the assignment. You don't have to do all the function definitions to do this, by the way. You could type just in curly braces here, cos 3t sine 5t, tab over, outside the curly braces, t goes from 0 to 2 pi, and you get the same graph. But it's handy to define functions, so you don't have to, it saves typing, you might say. But what I want to do now is I want to visualize the motion too. One way to do that is with manipulate. This is not something you're going to make a printout for because it's an animation. So no need to use manipulate for your assignment. I'm just going to copy and paste this code and put it inside the manipulate, though I do have to make some adjustments. So I'm going to have to copy and paste this, put it in the manipulate. So I'm really composing Mathematica functions here. And I don't know why I got rid of my last square bracket there. I must have highlighted the wrong thing. Notice this square bracket is pinkish. That means it's missing an n square bracket. So you need to close it off. That's one of the most common mistakes people make in Mathematica is forgetting things like that, or forgetting commas, or forgetting square brackets, or curly brackets, or capital letters. So this is going to make an animation in the parametric plot to see the motion. But I need to do some other adjustments. I need to put a comma here after the parametric plot that's inside the manipulate. The manipulate always has at least two inputs separated by a comma. Whatever's being animated first, and then a comma, and then whatever your animation parameter is. What's the animation parameter going to be? Oh, how about the letter B? Why did I choose a B? Because it's going to be the right endpoint of my interval that I'm plotting it over, and then I'll make that right endpoint increase, and that'll make the curve get traced out. So this is not as ideal as a calculator for graphing parametric curves, but it's still what we've got to do. I want B to go from 0 to 2 pi effectively to see the curve get traced out. But if I put a 0 and a 2 pi, it doesn't quite work. Because if I put a 0 to start with, it tries to graph it from 0 to 0, and it doesn't like that. So I start by picking a number just barely bigger than 0 like that. And then put a comma and 2 pi. Escape, P escape makes a pi, or capital P-I. It's still not going to be quite ideal. I'll go ahead and enter it as is. We're still going to make some adjustments to it. One thing that's not ideal is it makes the plotting window kind of funny to begin with. It's choosing the plotting window, and it makes it bigger in the end. But I would like to keep that plotting window fixed. That can be done by adjusting the code inside the parametric plot. So before its final square bracket, put a comma, and then plot range with a capital P and a capital R, arrow. To make an arrow, put a minus sign and a greater than sign. And oh, if I put, say, a 1.2 or something, that'll be good enough. what that's going to do is it's going to make it choose the X min, X max, Y min, and Y max to be plus or minus 1.2 in both cases. Then we're looking at the entire window right from the start. Play it, and there we go. There's the motion. You can slow the motion down, make it more smooth. And you do see as you watch this, in the straightaways, like now, it's going kind of fast. And in the corners, so to speak, it goes slower. The sharper the corner, the slower it goes, like right now. Then it speeds up. So the speed of the motion is not constant. And one of the things we're most interested in is finding that speed function. It's not a constant function of t, and using that speed function to find the distance traveled along the curve, which is also called the arc length of the curve. But this curve obviously does cross itself many times. It's a self-crossing curve. Those who were in difficulty with linear algebra in the fall and who will take it next spring, in those kinds of situations, your parametric curves in what we call the phase plane did not touch each other. But here, it is crossing itself. That can happen in general. Okay. So we want to analyze that kind of motion. We are going to move toward that. And it'll come toward a climax with the modeling perspective in chapter 11 and 12, I believe. I think it's just chapter 11. Just chapter 11, actually. We'll try to understand the motion deeply in terms of understanding how the acceleration is acting. What is the acceleration vector doing? It's not like uniform motion along a circle where the acceleration vector is pointing straight toward the origin, the center of the circle. It's not that simple. It's a more complicated kind of acceleration vector, but we can understand it if we use these kinds of ideas, okay? We also have to bring in vectors into play. And if you think about it, understanding the acceleration in such a situation is pretty important because the acceleration is going to be directly proportional to the force. The net force you feel as you're driving your car around the Lissajous curve in a parking lot or something, or if that represented some roller coaster. I mean, if we did a three-dimensional version of it, be some roller coaster going around. The acceleration, if you can model the motion, you can model the acceleration, and that means you can model the net forces on the object as it moves. Of course, a roller coaster's also got the extra complication of having more than one car that are attached. So it'd be simpler if you're just focused on one car on the roller coaster. To build up toward that, though, we need to backtrack now and talk about simpler examples like linear motion at both a constant and non-constant speed. Model linear motion. I'm realizing we only have 20 minutes left, so we have to go quickly here. I hope it makes sense that certainly something that should work to model linear motion is if both f of t and g of t are linear functions. Yeah, that'll work. X equals f of t, y equals g of t are linear functions. What letter should I use? Well, it doesn't really matter. Maybe at plus b for f and ct plus d for g. This will model linear motion. What kind of linear motion? If you imagine time to start at time 0, we typically do, one thing you can say about the motion is that at time 0, you're at the point BD. A, B, and C, A, B, C, D, and B, or A, B, C, and D are constants. They don't have to be positive, they could be negative. Notice that at t equals 0, you are at the point, let's assume we're in rectangular coordinates unless said otherwise, with rectangular coordinates BD. Also notice that the rate of change of x with respect to t, f prime of t is a constant a, and the rate of change of y with respect to t is a constant. It's the constant c. And in fact, those are constant for all t. For this motion, your rate of change in the x direction is constant and your rate of change in the y direction is constant. If both of these are positive, if a and c are positive, the motion is to the northeast. X and y are both increasing over time. If a is positive and c is negative, the motion would be to the southeast. X is increasing and y is decreasing. If a is negative and c is positive, x would decrease and c would increase. The motion would be to the northwest. And if they're both negative, the motion is going to be to the southwest. I mentioned last time that the slope of a general parametric curve can be found, slope here, dy dx, in the xy plane as a ratio of derivatives with respect to t. dy dt divided by dx dt. In general, that's a function of t. But for this example, it's a constant function. dy dt is c, dy dx dt is a. So the slope of the curve is c divided by a, as long as a is non-zero. You can see it's these two situations that have positive slope and these two situations that have negative slope. In these two situations with positive slopes, a and c have the same sign, so their quotient is positive. In these two situations with negative slopes, they have opposite signs, so their ratio is negative. That's a constant for this example, but in general, for general parametric curves, this does depend on t. It's a little weird to say dy dx depends on t, but it's not so weird because of the fact that x and y themselves ultimately depend on t, including in the general case. If you wanted to model motion starting at a certain point at a certain time and ending at another point at another time, say you're here when t is 0 and here when t is 5, and you're modeling motion along a straight line at constant speed from this point to this point, what would I do? Well, essentially, I'd use these kinds of equations and try to solve for a, b, c, and d using the given information. There are tricks of the trade that allow you to solve pretty quickly, including just making graphs of x and y individually. Let's go ahead and figure out some numbers here. Let's pretend this is 7 there and 2 here, and this is 3 and 8. So this point has rectangular coordinates 7, 2, and this point has rectangular coordinates 3, 8. Probably the quickest way to solve for a, b, c, and d is not to plug all your numbers in and to solve a resulting system of equations. You could do that by plugging numbers in. I mean, t equals 0 and t equals 5 into those equations. Might be quicker to figure out what graphs of x and y versus t look like individually. X is a function of t and y is a function of t. If you can figure out what these graphs look like, you can figure out their equations pretty quickly from the slope-intercept form, and that'll help you figure out the parametric equations. X in particular goes from 7 down to 3 as t goes from 0 to 5, so it's a straight line like that. Looking at the first coordinates here, the 7 and the 3. Y goes from 2 up to 8 as t goes from 0 to 5. The slope of this one is rise over run rise is -4, run is 5, -4/5. And the slope of this one is 6/5, -0.8 and +1.2. That tells you what the coefficients A and C are here. The derivative of this one is -0.8 and the derivative of this one's 1.2. Then it's left to find B and D, but those are the intercepts. The vertical intercept for this one is 7. The vertical intercept for this one is 2. There we go. We've quickly figured out the equations. What would they be? For this motion, X would be 7 minus 0.8t, and Y would be 2 plus 1.2t. You could also write it in terms of fractions if you prefer. As t goes from 0 to 5, that would model the motion that I specified, going from this point to this point at a constant speed as t goes from 0 to 5. The constant speed, by the way, I'm not going to derive it, but the constant speed turns out to be the square root of dx dt squared plus dy dt squared. It's effectively an application of the Pythagorean theorem to the velocity vector. In this case, that's square root of -0.8 squared plus 1.2 squared, square root of 0.64 plus 1.44, square root of what? 2.08. About 1.442. If your units of distance are in meters and time is in seconds, that'd be in meters per second. Could we model motion along a line at a non-constant speed? Let's just go ahead and type these functions in here. F of t is 7 minus 0.8t. G of t is 2 plus 1.2t. Probably not best for you to try to type with me here. Just watch and listen here. R of t is f of t comma g of t. Let's copy and paste this code here and make appropriate changes. I want to make my plot range bigger to see the entire curve, say up to 10. B is going to go from just barely bigger than 0 up to 5. Should see the motion here. There it is. Constant speed. What if I wanted to make this not constant speed, but along the same line? I could, for example, this is just one example of something I could do. Replace the t with t squared, for example. It'll be along the same line, but it'll not be a constant speed. If I do that, though, to end at the same spot, I got to go from, instead of up to 5, to square root of 5. Now watch the motion. It's not constant speed. It starts out slow, but then it speeds up, going faster and faster. That's motion along a straight line. What about motion along a circle? Certainly the most basic example is the unit circle, parametrized by the definitions of cosine and sine in terms of the unit circle. X equals cos t, y equals sine t, and notice they have the same frequencies there. If you trace out this, it'll be the unit circle starting at the point 1, 0 when t is 0, going counterclockwise at a constant speed. It'll be at the topmost point when t is pi over 2, the leftmost point when t is pi. Down here, it's when t is 3 pi over 2, and then it's back to where it started when t is 2 pi. And then the cycle repeats. That's the most basic way to parameterize the unit circle based on the definition of cosine and sine. And it does parameterize the unit circle because x squared plus y squared is cos squared t plus sine squared t is 1 for all t. So it doesn't matter what t is. You're on the unit circle, and in fact, you are parametrizing the entire circle at a constant speed. What is that constant speed? It is certainly a constant speed, but what is it? It's got to travel 2 pi units of distance, the circumference, in 2 pi units of time. It's 1 meter per second. It's at a unit speed. Like this. Just copy and paste and make adjustments. Change this to cosine t. Change this to sine t. Enter it. Let b go up to 2 pi. Change my plot range again, back to, say, 1.2. Here's the motion. Constant speed. Circular motion. I don't know why it stopped there. Seems to, okay, we're stalling. What if I wanted to make this non-constant speed? Get rid of this. I could once again replace t with t squared, for example. Now it speeds up. It's going slow at first. I want to go up to square root of 2 pi. Again, replacing t with just t squared is just one example of something I can do. There's infinitely many choices I could make there. I could do t cubed, square root of t. Watch again. It starts out slow, but then it speeds up because t squared's concave up. That's why that's happening. I could make the motion go backwards the other way, clockwise instead of counterclockwise. I could replace t with negative t. Make the motion go counterclockwise, starting at the same point. I could make the motion elliptical instead of circular, though I need to change these functions. Maybe 2 cos t and sine t. Now the graph is an ellipse. And the fact that I have a 2 here means the amplitude, so to speak, in the x direction is 2, and the amplitude in the y direction is 1. The equation of this ellipse, by the way, if x is 2 cos t and y is sine t, x squared over 4 plus y squared, it's going to be 4 cos squared t over 4 plus sine squared t. The 4's cancel, leaving me with cos squared t plus sine squared t equals 1. The equation of the ellipse that we parameterized is, in x and y coordinates, is x squared over 4 plus y squared equals 1. That's a 1 there, not an 11. There are various things you should be able to do that I haven't had much time for here. Let me just try to end class by hinting at a couple examples that you should make sure you study in section 9.2 if you haven't already. Sometimes parametric curves can cross themselves. How do you figure out where? With these coordinate functions, turns out to cross itself. Oops. I guess I need to go further the other way. There's a static plot of it. I believe the motion, you can't see my hand here, is this way and around this way. It does touch itself. How do you figure out where this is? The algebra is complicated, but the idea is not too bad. You want to, if it's going to cross itself like this, there are 2 separate times where it's at the same point, same xy coordinates. So effectively, you have to solve for where f of s equals f of t and g of s equals g of t. You want both the x and y coordinates to be equal at 2 separate times, call them s and t. Understand the concept here? We're after 2 separate times, s and t, where the x coordinates are the same and the y coordinates are the same. This is a system of equations in two unknowns, two equations, two unknowns. Nonlinear equations, these are nonlinear functions. In general, such systems are difficult to solve. But in this one, it's possible. Ignore this one. You're getting s is -1 and t is 3, or s is 3 and t is -1. What that means is 3 and -1 are solutions. F of 3 and f of -1 are both 2. G of 3 and g of -1 are both 6. You're at the same point with x, y coordinates 2, 6 at these two separate times, -1 and 3. That's what this means. Now, if you try to do this algebra by hand, it is a pain. Okay. Will you have to do things that are such a pain because you got to end up solving, like, deal with cubics? Do you have to do such a problem by hand? I don't remember. I have to look at the problems and we'll see. Okay. Also watch out for problems about eliminating the parameter, but we're out of time.